Hello, everybody. This is Randy. Today I'm going to talk about gasket simulation in Abaqus Standard. This talk will be useful to people who want to simulate something like you see here in this animation. And after the talk is over, we will have some question and answers, but if you want to contact me by email, you can see my email address here. So let's go ahead and get started. So first of all, what is a gasket? I think everybody has a feel for what a gasket is. Here you can see examples of gaskets, head gaskets, valve cover gaskets. The main purpose of a gasket is to seal between two mating surfaces or flanges. The gaskets can have a complicated geometry, and there could be a rather complicated behavior that is the mechanical response in the thickness direction. Okay, so that's a gasket, and so gaskets need to survive the mechanical loading, the thermal loading. They need to be resistant to whatever materials that they may come into contact with, and they need to provide that seal between the two flanges. So why would you use a gasket? Why don't you just clamp the flanges together so hard that you don't have to worry about sealing? Well, that might not be such an economical thing to do. You might need a lot of bolts. You might need to machine the flanges to make them very smooth, which would be more expensive. You could weld the flanges together, but then you couldn't easily take it apart. Sometimes I will call gaskets seals. Some people use the term seal only for applications involving, moving sealing surfaces, like a seal around a rotating shaft. But I call those dynamic seals, and I call everything else a seal or a gasket. I apologize if I'm being imprecise there, but that's what I do. So some gasket applications include a lot of things in internal combustion engines, like head gaskets, exhaust manifold gaskets, valve cover gaskets, intake manifold gaskets. Oil filters have a seal around them. So when you screw them on, the oil doesn't leak out. Medical devices may have various kinds of gaskets or seals. Cell phones might have one seal around, the cover, so that when the cell phone contacts liquids, it doesn't cause a problem. Fuel cells have various kinds of seals in them. There are a lot of industrial applications, et cetera, et cetera. My coffee cup, you can see here in the picture, has a rubber gasket or seal in the lid, so that when I screw on the lid and then drink from the the hole in the coffee cup, then the hot coffee doesn't pour out onto my shirt. So there's a lot of applications for gaskets or seals. Some gasket types are metallic gaskets, and then there are non-metallic gaskets. And you can see the various materials here: steel, aluminum, copper, and so on. I was watching a video of a person working on a really old internal combustion engine, and the head gasket was basically a thin copper sheet. So that was the gasket in that case. And then you can have all kinds of non-metallic gaskets, like made out of fibrous material, some sort of composite type materials, molded rubber, like the seal in my coffee cup lid. You might have something like graphite serving the purpose of a seal or a gasket. Why is a gasket analysis a challenge? Well, that's really the idea behind the talk today. It's a challenge. So, but why is it a challenge? Well, you may have a complex geometry, and the dimensions of the gasket are kind of, out of whack. The in-plane dimensions are much bigger than the thickness. So in order to build a mesh in the normal way you do when you're doing finite element analysis, you end up with a lot of elements through the thickness. And then because of the extent of the gasket, then you end up with a lot of elements overall. And then not only that, but you might have a complicated through thickness behavior that you have to account for. And that might mean some sort of sophisticated material model that you put in, and you have to calibrate the material model, and then you have to have the complicated mesh. You end up with a rather elaborate finite element model just for the gasket, and then the gasket goes into some other model which might have millions of degrees of freedom, and now you're just compounding the size and complexity of the overall model by modeling the gasket in the usual way. So the gasket has to be considered together with the rest of the structure. If you're just simulating a gasket by itself for some reason, then maybe you could get away with using the regular finite element methods. But you really need to do the sealing analysis, and that involves the compliance of the flanges and everything. So you have to consider everything overall. And then you also need, in many cases, effective treatment of the fasteners that are clamping the flanges together. So all of this together makes, simulating gaskets in the usual finite element methods a challenge. So what do we do about that? Well, that's what I'm going to talk about. Abaqus has a special element called a gasket element, or actually it's a family of elements. And these elements were designed to improve and simplify the meshing and the constitutive modeling. So the elements are going to have a complicated thickness behavior in terms of the mechanical response through the thickness, but it's going to be an intrinsic part of these gasket elements. We're not going to use regular material modeling to build the complex through the thickness behavior. Now, Abaqus Standard also has something called pretension section, which provides a convenient approach to doing the fastener loading in many cases. Abaqus Standard and Abaqus Explicit both have connector element technology, which is an alternative to using pretension section in some cases. So you could do that as well. But a lot of people like this pretension section option. Here is a excuse me, elliptically shaped ring that's going to serve as a seal. And this mesh is rather refined to capture the mechanical response of this seal. You can see down here in the bottom in the green box, this mesh has 68,112 nodes. The picture at the top left shows a material calibration in our material calibration app. So I'm just putting that here to show you that the material here is a complex material that's modeled with something called the parallel rheological framework. So this is all rather complicated, and that's just the gasket. Now, suppose that this was in some sort of larger simulation that had, say, 10 or 20 of these seals in there. So you take 68,000 and multiply by, say, 20. That's a lot of nodes just for these rather or seemingly inconsequential seals that we want to put in there. So that seems, like overkill in terms of model size and model complexity. So let's see what we can do with the gasket elements in a situation like that. So in Abaqus, we have two basic formulations of gasket elements. And gasket elements start with the letter G for their type label. and then you have some other letters and numbers there represented by the X's here. So the categories that we have are the regular gasket elements, as I call them. That would be these elements here. And then we have what are called normal only gasket elements. And regular gasket elements have the regular 3 degrees of freedom per node if you're doing 3D. But gasket elements in the normal direction only have a specialized 1 degree of freedom that's in the thickness direction. These days, I see people using the regular gasket elements more often. The regular gasket elements have an uncoupled membrane transverse shear response. It's uncoupled from the thickness behavior. We have a couple of options for defining the thickness behavior, and we'll see those as we go along. Down here at the bottom, you can see a picture of a gasket element. It's really kind of analogous to a shell element in many ways. You have a normal direction and you have some in plane directions or in surface directions. Both gasket element formulations can be used to model 3-dimensional axisymmetric and planar problems. Here you can see an example of what are called area gasket elements, GK3D8. So gasket 3-dimensional with 8 nodes. You could also have the normal type, and there's a 6-noded version of that. And it's almost always the case that gasket meshes have 1 gasket through the thickness, as you see here. The different colors in this gasket mesh represent different gasket behaviors, as they're called. So the red mesh has a different gasket behavior from the green mesh. Gasket elements can be used in static simulations, dynamic simulations, frequency simulations, or frequency extractions. Gasket elements don't really have a mass, so that's not usually a problem because the gasket makes up a very small percentage of the mass of the overall structure. Dynamic gaskets are gaskets that include viscoelastic properties. And there are also gasket elements that have temperature degrees of freedom at their nodes so that you can transfer heat through the thickness direction. Gasket elements are formulated for small strains and small displacement calculations. But the thickness change can be substantial compared to the thickness. Gasket elements should not rotate because the gasket normal direction doesn't change. So here are the different kinds of gaskets. We have 2-noded gaskets, 4-noded gaskets, 8-noded gaskets, and so on. And there are line gaskets, area gaskets, and so on. This is probably the most common type of gasket element that is used, the GK3D8, which looks like a brick element C3D8, except its integration points are in the sides instead of inside the area or the volume of the element. Area elements like GK3D8 have nodes defining the face on the top and the bottom of the gasket. Surfaces can be defined on the top and the bottom of this type of gasket. The local 1 direction for the gasket goes from the bottom to the top. So that again is similar to a shell element. So in this picture here, the bottom face is defined by 1, 2, 3, 4 nodes, and then the top is 5, 6, 7, 8 nodes, and then the normal goes from the bottom to the top, and that defines the thickness direction. there's really nothing going on with the sides of a gasket element. It doesn't really have sides in like a brick element would have. It has a top and a bottom, and that's where all the interesting things happen. The thickness of the gasket is calculated from the nodal coordinates by default. You can override the thickness defined by the nodal coordinates if you so desire. Um, the user can specify the normal direction if you want to do that. I don't see that done very commonly. People sort of rely on the nodal definitions. You can see the various properties of these gasket elements in the DAT file. The DAT file has a lot of information on a lot of things in the Abaqus model. If you print it out with the star preprint, that's an option that you can use. Gasket element connectivity can differ from solid element connectivity. For GK3D8, it seems to be about the same, but you have to be careful because the first 4 nodes in that element definition have to define the bottom of the gasket. So if you mess up and don't get the numbering right, then the gasket normal direction, which is very important, will be incorrect. Fortunately, preprocessor Abaqus CAE supports gasket elements. You can, make a gasket mesh with the correct thickness direction. But in some cases, you might have to rearrange the nodal ordering on the element definition to get the thickness direction correct. So there is an option for switching around the nodal ordering to get the gasket normal correct. So here's an example. Let's look at the right-hand picture first. And this element is defined 1, 2, 3, 4 in its definition, which is okay for something like a plane strain element or a plane stress element, CPE 4 or CPS 4. But a gasket element, we want the thickness direction to go from the bottom flange to the top flange. So it has to be connected up in a crisscross fashion, 1, 2, 3, 4. And if I remember correctly, this is similar to really old school contact elements that people used to define. So if you use the numbering on the right and you really want the numbering on the left, and that gets goofed up, unless you say solid element numbering equals 4 to tell Abaqus that the 4th side of this element defined as a ordinary element is really the bottom of the gasket. So you have to, pay close attention to that. Always verify the properties of your gaskets before you use them in a large, complicated model. There's nothing, more annoying than to run a large model and find out that your gasket is all messed up. So we want to model our complex gasket with a simple mesh. And down here, you can see an example. The picture on the left down here with the section through it is our complicated gasket geometry. And if we look at section AA, it has these bumps which are intended to, form the sealing pressure. But there's a region in the middle that has a gap. So I have to push the bumps down substantially until I hit the body of the gasket. So we try to model this cross section with a cross section as shown here at the bottom. And this would be our gasket mesh. So how are we going to account for a gap? How are we going to account for these geometric bumps? Well, what we do is we push down on this section and figure out how much pressure it takes to close down on these gaskets. And then we simply define into the element itself the so-called pressure closure curve. And the pressure closure definitions in Abaqus allow us to account for the complex, mechanical response in the thickness direction, including the effect of the gap. And because the middle of the gasket cross-section is different than the bumps, we have to have different behaviors defined to account for the bump, or the bumps in this case, and then the gap in the middle. The gaskets can be defined in Abaqus CAE. You can see that here. You won't see a blank box here when you look at the Abaqus CAE tree. I blanked that out because I thought what was under this box is kind of confusing, so I didn't want to show that. But it is something that you can define in Abaqus CAE. And gasket behavior is supported in the material definition app and the 3D experience platform. And you can see that here. All right, so we want to have, and I've said that we can have this complicated thickness behavior. What exactly is that and how do we define that? Well, the key word for it is called gasket thickness behavior. And we have two basic types. One type is called type equals damage. And this defines a nonlinear elastic response that may include the effect of damage. A recent enhancement to this kind of thickness behavior is the ability to change the interpolation to more accurately capture the unloading response in some certain situations. So if you have a gasket that seems to be misbehaving, meaning that it doesn't follow the curves that you put into it, then you might check out this new option. But you can see what you get with this kind of thickness behavior. It's very similar to, or looks much like the um, damaged elastic response that you can get in hyperelasticity. That is the Mullins effect. So if you load the gasket up to point B and then unload, if you've defined damage unloading, then you get unloading down to back to A. So it is an elastic response. And then when you reload, you go up the damaged curve and then continue on and so on. So for this type of thickness response, you do define a primary loading curve, and then you can define a series of unloading curves. If you unload from an in-between pressure, then Abaqus will interpolate to get that unloading behavior. The other type of behavior that we offer is elastic plastic. And in this case, when you unload, you have a plastic or a residual closure. That is, the thickness has been permanently changed and is smaller. And you can see that here. And this would be analogous to an elastic plastic material where you load and go out along the hardening curve and then unload. You have this plastic closure that occurs. And then when you go back up, then you continue on just like you would for an elastic plastic material. And there are various options for defining the yield point, which is point B in this figure. So the default onset of plasticity is set up by this 10% rule. So if the slope of the loading curve changes by more than 10%, and that's called a yield point, but you can change that. You can specify what you want. Probably the type equals damage is the least troublesome of the two thickness behaviors. If you don't unload the gasket all the way, you might not see much difference between the damage and the elastic plastic behavior. Some people may argue with me on that point, but I would argue that that's the case. What about other behavior options? You can associate a material definition with the gasket section. You can even associate star creep. This is not common to do this. I don't see this done very often. Gasket elements in Abaqus Standard allow direct specification of dynamic stiffness and damping as part of the gasket thickness behavior specification. Okay. Here's an example just to show you what you can do. Here I have my coffee cup seal inspired this situation. However, in this case, the uh, profile of the gasket is an ellipse, and you can see the cross section. It's not exactly my coffee cup gasket probably, but it's similar to that. And I want to push down on this seal. And so this is my geometric situation. I have these two flanges and my seal is in between. So you can see the situation in this example. So I can build a two-dimensional cross-section of this seal, and you can see that here. This is a plane strain simulation. The cross-section undeformed is the mesh, and then the green outline is what happens when I push down. And it does what we expect. The bumps get pushed down, and maybe it does something that we didn't expect. The material folds over on itself in this location, which and then there's self-contact defined here. And that seems like that might present a problem if I were to run a large three-dimensional simulation. So that's the behavior of our cross-section in the plane strain case. But we don't have a plane strain case. We have an elliptical profile here. So how would I get my gasket properties? Well, one thing I could do is test the gasket and push it down in a test machine and extract pressure and closure curves, and that's actually done by some users. I don't have a test machine, so what I did was a plane strain simulation. In fact, that plane strain simulation that I showed there, and I tracked the force for my plane strain simulation, and I tracked the contact area. So Abaqus has output variables which will tell me the area that's in contact, so I can plot that. That's what you see on the left hand side, and then of course I have the force that's pushing it down, so I can get the the pressure closure behavior on one of the bumps, and I can get the area change on one of the bumps. And you can see here that Abaqus actually has options for inputting how the gasket area changes, and this would be for the line gaskets. And so I can put these into my gasket behavior definition. So what does that do for me? Well, let's see. Here you can see on the left-hand side an actual 3D simulation in Abaqus Explicit, where I simply took the actual geometry, meshed it with C3D8R elements, and then I squished it between those two plates. On the right-hand side, you can see the analogous gasket simulation. The line gaskets, those are looking like shell elements turned up on their edge. And so I represent the gasket bumps with these two line gaskets. Now the picture on the far right is the contact pressure along a path through the bump. And this is what that looks like. And if I take this curve and find its average, the average pressure on that bump is 4 MPAs. And you can see from my, it's 3.8 MPAs. The gasket, the analogous gasket analysis gives the pressure in that area as 4 MPAs. So that looks pretty good. I lose resolution. I can't tell you how the pressure changes across the contact, but I can tell you the average sealing pressure. So that seems pretty good. The simulation in the middle here seems much less complicated than that full-blown three-dimensional simulation. In fact, you can see here that in the 3D model, just like in the 2D model, I get this creasing behavior, which can be problematic for Abaqus Standard, which is why I chose to run the simulation in Abaqus Explicit. I didn't want to, fight with any creasing inside Abaqus Standard. I could probably do that, but in Abaqus Explicit, this is no big deal. Okay, so here's the amazing thing. The line gasket model produces this useful sealing result at much, much less expense. Abaqus Explicit was used for the 3D model, as I said, to avoid the convergence problems in Abaqus Standard when I formed these creases. And here you can see on the left, the 3D seal problem ran in 1 hour, 22 minutes on 14 cores. In Abaqus Explicit, the number of degrees of freedom was 2.4 million. The line gasket model ran on my laptop in 35 seconds on 2 cores in Abaqus Standard, and I only have 4,164 degrees of freedom. So that seems pretty good. Now, if I just wanted to simulate that rubber component by itself, maybe I would choose to do this in Abaqus Explicit. But if I want to put that seal in, say, in my coffee cup, and then deform the coffee cup, and the coffee cup itself has 5 million degrees of freedom, and now I'm adding on 2.4 million more because I have my gasket, maybe I would choose to use the line gasket model. It's much more efficient, and it is, or does seem capable of telling me useful information about the sealing pressure. So how do I actually put gasket elements into a mesh? Here in this example was rather easy. I really didn't have much of a structure except for the gasket itself. You can attach gasket elements to other parts of the model through contact pairs or simply by sharing nodes, which is uncommon. Using MPCs is also uncommon, but this is possible. The most possible or the most popular way, of putting the gasket into the rest of the mesh is through contact pairs and/or star tie. And it's also very common and most common to simply have one layer of gasket elements. I don't recall seeing a gasket model that has more than one layer of gaskets in the thickness direction. I have seen gasket behaviors defined by compression testing. And you might do that. Of course, you have to do testing to get those properties. What do I look at in the output when I have a gasket element? Well, the sealing pressure is called S11. If you're doing that would be for an element like GK3D8. CS11 is the pressure for a line gasket element, like I used in that coffee cup example. That's not really a coffee cup because it's elliptical. That would be an interesting coffee cup. It would be hard to screw the lid on if you had an elliptical lid, but I guess you could push it on and snap it on. E11 is the gasket closure, which has units of length for the gasket element. And then you can get some other variables out of the gasket. But by far the most common two to look at are S11 and E11, which are the pressure closure. You can create your own user output variables using star user output variables, and then the subroutine UVARM. And sort of off the topic here, recent Abaqus releases support Gfortran if you're running on Linux. So Gfortran, of course, is something that comes with Linux. So if you want to do subroutines, you don't have to worry about getting the iFortran stuff. You can use Gfortran. But you have to have the version of Abaqus that supports Gfortran. Practical tips for gasket element usage. You need to verify gasket behavior and convergence characteristics. So set up a single gasket element model to verify the gasket behavior. Just have one gasket element, push it down, unload it, make sure that the pressure closure behavior, looks right. As I said earlier, it's annoying to find out that your gasket behavior is not what you thought it was after you ran some really large complicated model. This would be a good tip for any kind of novel feature that you put into an Abaqus simulation. So if you have a complicated material model, make sure it's doing what you expect it to do. If you have a complicated connector element behavior, verify it with a simplified model. If you're applying an acceleration and you think it's going to slightly deform the structure, but starts deforming it largely, maybe you can test it or should have tested that acceleration load with the small model to make sure it looks right. You can set up a test with the entire gasket. This is kind of what I did with that line gasket example. I really just had a line gasket being compressed through by two plates. So you can compress your gasket, and make sure that the gaps are correct, so there's no sealing pressure on the body of the gasket until the gaps are removed and things like that. There are some, technical issues with gasket elements. Things like unsupported gasket elements can cause a problem. So what is an unsupported gasket element? This is a gasket element that's hanging out in space. So some gaskets, when you install them, there is some portion of the gasket that's just, spanning across a gap of some sort, a hole, in this flange. So gasket elements that are unsupported can cause problems. There are options, or is an option called stabilization stiffness, which is an option for star gasket section, which is intended to deal with this situation. If you do a data check, you can find the unsupported gasket element nodes by looking for the no intersection text in the printed output file. To prevent numerical ill conditioning problems, when there is an initial gap, a small amount of stiffness is applied to the initial gap. You can see that here. By default, Abaqus will take the slope, the actual slope, when you get beyond the gap, and multiply that by 0.001. And this is the so-called gap stiffness, or that's what I call it. So even though you have a gap, it does have some stiffness. And if K is big enough, then 0.001 times K might be too big. So, and then you'll have some noticeable sealing pressure on the body of a gasket, say, even though there should be no sealing pressure. So you might have to reduce this factor. And you can control it with this tensile stiffness factor option, which is I think it's part of gasket thickness behavior. Oh, okay, so let's look at another example. This is a more elaborate example that comes from the Abaqus documentation. And this example has a coolant manifold cover. There are a couple of bolts, and then there's a manifold below that. And there's a gasket compressed in between. And over here to the right, you can see what the real gasket cross-section looks like. It has a body, and then there's a sealing bump on the top of it. So the idea here is to bolt down the bolts. The bead has a pressure on it, and that forms the seal so that the fluid that's flowing here doesn't get out. Of course, we're not going to actually have a fluid flowing here. This is a mechanical analysis. So the gasket in this case is modeled with gasket elements. In fact, that's the picture that I showed earlier with the body region and the other red gasket region, and those had two different behaviors. This is a model with symmetry, so it looks chopped in half here. And we're going to have a series of load steps. This is the gasket geometry, and the thickness here is chosen so that we are accounting for the height of the bead. And so we put that in, and then we segregate or partition the mesh so that we can define different behaviors for the part of the gasket that has the bead and then the body of the gasket. Okay. An accurate description of the pressure closure behavior of the gasket is essential if this model is to predict the performance of the gasket. Since the paper foam is made of a highly compressible material, there is an insignificant amount of coupling between the thickness and in-plane directions for this component. We developed the pressure closure behavior from a uniaxial test, actual test. The silicone bead pressure closure relationship was captured also from a uniaxial test, and then we did some sort of magic to get the overall behavior of the two stacked up. If you have experimental data, then you can do things like this. If you don't have experimental data, then you might do what I did back with the coffee cup seal, and that is do some sort of extra FEA on the cross section to get the gasket response. So here is what the gasket definition looks like. We have, this is for the one section of the gasket, which is the gasket body. And so we have a definition of the gap that's shown here. And then we have the gasket behavior and give that a name. And that name shows up here in the gasket section. And then we have our gasket thickness behavior in the loading direction. This is an elastic plastic response or type. And then down here, we have the unloading. We only have one unloading curve shown. You can have multiple unloading curves, and they are for an elastic plastic unloading. They are grouped by the residual plastic closure. And the point that's at the end of the unloading should match up with one of the points in the loading curve, as you see here. Now, this point here is also on the loading curve. We only have one unloading curve, and so if we unload in between, Abaqus will interpolate. Gasket behaviors, I believe, are extrapolated on the loading side. Here is the behavior for the body with the bead, and it is different, but the numbers are different, but the format is basically the same. So the first behavior was for the green part of the gasket, and then this behavior is for the red part of the gasket. So we're going to do an assembly with the bolts. So these bolts have a surface which cuts through them on the free length in between the head of the bolt and the part down below where it's attached to the manifold. And this surface that cuts through the shank of the bolt defines a pretension section, then we use the pretension section option in Abaqus Standard to load the bolt. Basically, the pretension section changes the length of the bolt so that it gets shorter. And then because it's in contact at the top and attached at the bottom, if we try to make it shorter, it develops a tensile load in the length of the bolt. Pretension sections are associated with a special node called the pretension node, which should not be in any other feature in the mesh. And then the pretension section node has a special degree of freedom, which tracks, what's going on with this pretension section. So we have load history applied, and this makes use of the ability in Abaqus to have multiple load steps chained together. So in step 1, we're going to pretension the left bolt. In step 2, we're going to pretension the right bolt, and then we're going to fix the tension in the left bolt when we do that. Step 3, we're going to fix the right tension, and then we're going to heat up everything and pressurize the interior cavity where this fluid would be. And then in step 4, we're going to decrease the temperature down to -40. And then in step 5, we're going to pump it up to back to 20 and then remove the pressure load. So we're going to look at 2 temperature extremes, and then we can get an idea of how our sealing pressure changes due to the mechanical loading of pressure and also the thermal effect. So here's the contour plot of the sealing pressure. I won't go into details on what all of the results are, but you can see as the time varies that we get different kinds of sealing pressure. And of course, this is going to be like the case with the coffee cup type seal. We're going to get an idea of sort of an average sealing pressure, which would be, maybe good enough. If we really need a detailed sealing pressure, maybe we need a more elaborate model than what is shown here. But this is an efficient way to get an idea of what's going on with the sealing pressure due to these changing loads. All right, so that is the presentation that I had today. So